In this video, we are going to discuss divisibility rules for 7. We shall prove them rigorously using modular arithmetic. So now let us learn some basics of modular arithmetic. A mod n is defined as the remainder when a is divided by n. For example, 17 mod 5 equals 2 because 17 leaves a remainder of 2 when divided with 5. A is congruent to b if a mod n is equal to b mod n. So 23 is congruent to 18, which is congruent to 8, which is congruent to minus 2 mod 5, because they all leave the same remainder 3 when divided by 5. If a plus b equals c, then a plus b whole modulo n is congruent to c modulo n. And similarly, if a times b equals c, then ab whole modulo n is congruent to c modulo n. If a is congruent to b mod n, then a can be written as b plus sum nq, where q can take the value of any integer. Now we can make two claims and prove them easily. These claims will come in handy and play a crucial role in the future. Claim 1 says a plus b whole mod n is congruent to a mod n plus b mod n. Claim 2 says a times b whole mod n is congruent to a mod n times b mod n. So now let us look at some examples before jumping into the proof. Take a second to realize that using these two claims, these all examples do in fact check out. For this proof, let us say that R1 equals A mod n and R2 is equal to B mod n. This implies that A1 can be written as R1 plus some integer multiple of n, and similarly B2 can also be written as R2 plus some integer multiple of n. Hence A plus B whole mod n is congruent to R1 plus R2 whole mod n. We can just ignore the mod n on the right hand side and hence the proof is complete. Proof for claim 2 is very similar and left as an exercise. Let us look at an example for mod 3. 5368 can be written as such after decimal expansion. Taking mod 3 on both sides and using claim 1 on the right hand side, we get the following. Now using claim 2, we get this lengthy congruence. Now by observation, we can see that 1000, 100, 10 and 1 are all congruent to 1 mod 3. Thus we can see that the sum of digits is congruent to the number mod 3. We can prove that the sum of digits is congruent to the number mod 3 for all numbers containing any number of digits. This would follow if 10 to the I mod 3 is equal to 1 for I taking values from the naturals. The inductive proof for this is being played on the screen right now, which I'm sure is easy to follow. Heading to mod 7, we can leverage the fact that 3 is a generator of class mod 7. This means that 3, 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th and 3 to the 6th are all different mod 7, none of them being 0. The animation on the screen shows the values of 3 to the I for I ranging from 1 to 6. Note that they are all different as claimed. Now using binomial expansion, we expand a plus b to the n mod 7. And with claim 1, we get the following expression. Now plugging in 3 and 7 for the values of a and b, we notice that for k greater than or equal to 1, the whole thing is a multiple of 7 and hence mod 7 of that would just be 0. This implies that 10 to the n is congruent to 3 to the n mod 7. Hence 10 is also a generator of mod 7. We just write the first 6 powers of 10 on the screen to make sure we're right. Now we have done enough to look at the divisibility rule for 7 in detail. My rule says that if you have a 3-digit number, for instance, Remove the leftmost digit and add 2 times of its face value to the remaining 2-digit number. This method almost always guarantees the number of digits to reduce. Let us take a random 3-digit number, let's say 117. We note that 117 is congruent to 5 mod 7 before starting with our algorithm. Now using the algorithm we get 117 is congruent to 19 mod 7 and 19 is congruent to 5 mod 7, hence it works for 117. Take another 3-digit number, let's say 651. We note that 651 is congruent to 0 mod 7. Now using the algorithm, we get 651 is congruent to 51 plus 6 times 2 whole mod 7. So we get that 651 is congruent to 63, which is congruent to 0 mod 7. Heading to 4 digits now, let us take 2476. We note that 2476 is congruent to 5 mod 7. For the 4th digit of the number, instead of 2, we have 6 as the scaling factor. Therefore, 2476 is congruent to 476 plus 2 times 6 whole mod 7. Hence, we get that 2476 is congruent to 488 mod 7. Applying this again for the 3-digit number 488, we get 488 is congruent to 88 plus 4 times 2 whole mod 7. Hence, 2476 is congruent to 96, which is congruent to 5 mod 7, which checks out. We can obtain the scaling factor of all digits by hit and trial. The table shows the first few scaling factors. I highly encourage you to see for yourself that it is periodic with the period 6. Let us run this algorithm for a 5-digit number using the scaling factors from the table. But why does this scaling factor work? And why does it happen to be periodic with a period of 6? There must be many similar questions you have, so let us try to answer them. When we write an integer in decimal representation, it is very easy to explain these results. Just split the first digit as shown on the screen by applying claim 1. Now using claim 2, note that en is multiplied by 10 to the n mod 7, which we can replace with a number from 1 to 6. That is the scaling factor. Hence, this is equivalent to removing the leftmost digit and adding a scaled multiple of its face value. Now it has a period of 6 because 10 to the n mod 7 has a period of 6. Now let us look at a corollary of this theorem. Take this big number. Split it into multiple parts, each containing 3 digits. In this case, 473, 687 and 451. Number them 3 to 1 respectively. Now add the odd numbered numbers and subtract the sum of even numbered numbers. Now take the old example of 93,284. Now we have to split it starting from the right, taking 3 digits each. So we get 284 and then 093. Label them as 1 and 2 respectively. Now we subtract 2 from 1 to get 191, which should be congruent to the number mod 7. This is like the divisibility rule for 11 but in base 1000 instead of 10. This is because 1000 is congruent to minus 1 mod 7. Now how can you remember the scaling factors? Here's how I do it. I call it the 264 rule. The 3rd digit is scaled by 2, the 4th by 6 and the 5th by 4. Now the 6th, 7th and 8th would be minus 2, minus 6 and minus 4 respectively, and the pattern repeats after this. You can use this algorithm in a slightly different way. Instead of doing it to the leftmost digit and adding it individually, we can do this to every digit at once and add them up. Take our good old number 93284 again. Now 93284 mod 7 is congruent to 84 plus 2 times 2 plus 3 times 6 plus 9 times 4 by our algorithm, which then reduces to 142, which is congruent to 2 mod 7. Now why do we stop when we arrive at a 2-digit number? This is because it is not efficient to use our algorithm because you keep getting 2-digit numbers after transformation. Note that the scaling factor for the 2nd digit is 3. So for example, 67 transforms to 18 plus 7. So then 25 transforms to 6 plus 5, and finally 11 transforms to 4. So it took us 3 transformations to reduce the number. The best part about this is that you can stop the transformation at any step and the modulo would have remained the same throughout. I hope you enjoyed this video and this inspired you to come up with divisibility rules of your own for other numbers.